In this video, we're going to look at the Pythagorean identities and how they relate to all 6 trigonometric functions. In particular, we're going to derive 2 variations of the classical Pythagorean identity, cosine squared theta plus sine squared theta equals 1, and we'll look at how to use identities and right triangles to find the remaining trig functions of an angle when we know one of them and some other information. We've previously seen the standard Pythagorean identity cosine squared theta plus sine squared theta equals 1, and that this is true for any angle theta. This is often used to be able to convert between sine theta and cosine theta. If we knew sine of theta for some angle theta, for example, we could use this equation to find the cosine of theta. There are different variations of this identity that can be derived from this one that involve the other trig functions. So we'll start here by looking at the variations of this equation that involve tangent, cotangent, secant, and cosecant. We can easily get a new identity from this one by dividing both sides of this equation by the cosine squared of theta. And if we do that, what we get is that we have the cosine squared of theta divided by the cosine squared of theta plus sine squared theta divided by cosine squared theta, and that will equal 1 divided by cosine squared theta. Cosine squared divided by cosine squared, of course, is just going to equal 1. Sine squared divided by cosine squared will be the tangent squared. We know sine divided by cosine is tangent, and if we square both of those, we'll end up with 2 copies of the tangent multiplied together, which is tangent squared. On the right-hand side, we have 1 over cosine squared, and we know 1 over cosine is the secant, and so this will be the secant squared of theta. All right, so we have this new identity that relates tangent squared and secant squared of an angle theta in the relationship that 1 plus the tangent squared will equal the tangent squared, or the secant squared. So this is another Pythagorean identity that follows directly from cosine squared plus sine squared equals 1, and therefore is true for all angles theta. And this will allow us to convert between tangents and secants. We can get another Pythagorean identity by starting with the original and dividing both sides by sine squared of theta instead of cosine squared of theta. If we do this, we end up with cosine squared theta divided by sine squared theta plus sine squared theta divided by sine squared theta, and that will equal 1 over the sine squared of theta. When this is simplified, our first term is cosine squared over sine squared, which will become cotangent squared. Sine squared over sine squared is 1, and the reciprocal of sine squared is the cosecant squared. And so we obtain another relationship between trig functions squared, specifically that cotangent squared of theta plus 1 is equal to the cosecant of squared of theta. So just like the original Pythagorean identity can be used to convert between sines and cosines, these variations can be used to convert between tangents and secants and between cotangents and cosecants. And among the 3, we notice that all 6 trig functions are present in exactly 1. In this example, we're going to suppose that the tangent of an angle theta is -4 and that the sine of the same angle theta is positive. We're being asked to find the remaining trig functions of theta. There's essentially 2 different ways that we can approach this problem. The first way is that we can apply the various identities that we've seen. Specifically, we would use the Pythagorean identities to convert from one trig function to another, as well as using the definitions of tangent, cotangent, secant, and cosecant as they relate to sine and cosine. Another approach is we could use right triangles in the plane. And this will involve thinking of the trig functions as ratios of sides of these right triangles. We'll actually look at how to solve this problem using both of these approaches. However, in either case, we're going to need to know the quadrant that this angle theta lies in. We can figure that out from the given information. So we're told here that the tangent of theta is -4, In particular, that is a negative number. And so we know that tangent is negative in quadrants 2 or 4. Tangent is positive in quadrants 1 and 3, and so because tangent is negative, we know that we cannot be in quadrants 1 or 3. We're also told that the sine of theta is a positive number, and we know this happens in quadrant 1 and in quadrant 2. And so that condition tells us that we're in quadrant 1 or 2. Now looking at these possibilities, the only quadrant that both of these would satisfy would be quadrant 2. And so this angle, theta, whatever it is, theta must be an angle in quadrant 2. And now that we know this, we can use either the identities or right triangles to determine all of the remaining trig functions. For our first approach, let's use identities to find the 5 remaining trig functions. We were given that the tangent of theta is equal to -4. And we know that the cotangent of theta is 1 over the tangent. This is true for any angle. And therefore, the cotangent is 1 over -4, or -1/4. So we can easily find the cotangent to be -1/4. In order to find another trig function, we're going to look at our Pythagorean identities. We know that one of those state that 1 plus the tangent squared of theta is equal to the secant squared of theta. We can substitute in -4 for tangent theta here and find the secant of theta. So this will be 17 equals secant squared theta. We take the square root of both sides. We have to remember to take a plus or minus here. And so the secant of theta will be either plus or minus square root 17. This is where the quadrant comes into play. We already saw that this angle was in quadrant 2, and in quadrant 2, the secant of an angle is negative. And so secant theta will be the negative square root of 17. Once we know secant, we can easily find cosine because cosine and secant are reciprocals of each other. And so the cosine will be -1 over square root 17. So now we have found the cotangent, the secant, and the cosine. What remain is the sine and the cosecant. And once we find one of those, the reciprocal will be the other. We can use a couple different options here with identities. We could use our cotangent value and the Pythagorean identity that involves cotangent and cosecant, or we could use the cosine value that we just found and the standard Pythagorean identity that cosine squared theta plus sine squared theta is equal to 1. When we substitute in -1 over square root 17 for cosine theta, we can solve this equation. So this will be 1 over 17 plus sine squared theta equals 1. We'll subtract 1/17 from both sides to get the sine squared of theta is equal to 16/17. We take the square root to get sine of theta equals plus or minus the square root of 16 over 17, which of course will be plus or minus 4 over the square root of 17. And to determine whether it is the positive or negative square root, we again return to our quadrant. This angle was in quadrant 2, and in quadrant 2, the sine of an angle is positive. So we have the sine of theta as 4 over square root 17. And lastly, we take the reciprocal to see the cosecant will be the square root of 17 over 4. Both of these are positive because the angle theta was in quadrant 2, which we saw before. And so here we have all 5 of the trigonometric values for the angle theta, whose tangent theta is -4, and whose sine is positive. And next we'll look at a second approach using right triangles, and we'll see that we obtain these same 5 values. in order to use right triangles to solve this problem, we need to think of the tangent of theta as a ratio of two sides of a right triangle. We're told that tangent theta is -4, and so we need to think of this as a ratio. And so I'm going to think of this as the ratio of 4/1. Of course, any other ratio that is equivalent to 4 will work as well. Recall that we know that this angle is in the second quadrant, and therefore I'm going to think of the angle something like this. Here's our angle theta, and notice that we have a right triangle formed by drawing a vertical down into the x-axis here. We know this angle in the triangle is the reference angle for our angle theta, and we know up to negative sign, the sines, cosines, tangents, and so forth are all the same for this particular angle. And so, in particular, we know that tangent of this reference angle is going to be 4/1, possibly a negative, which we're not going to worry about at the moment. We'll figure that out at the end. We're just going to look at the numerical part, which is 4/1. So the tangent is the opposite side, which is 4, over the adjacent side 1. And so this triangle here will represent our angle. We have the opposite side of our angle as being 4 and our adjacent side being 1. Once we know this, we can find the third side by using the Pythagorean Theorem. So 1 squared plus 4 squared equals h squared. And that will be 17 equals h squared. And therefore, h will be the square root of 17. So now we have all three sides of our triangle. So now we can use this triangle to write down all of our trig values. We know that sine of theta is the opposite side divided by the hypotenuse, so 4 over square root 17. We know that cosine theta will be the adjacent side over the hypotenuse, so 1 over square root 17. We already know the tangent was -4, so we'll skip that one. The cosecant of theta is the hypotenuse over the opposite, so square root of 17 over 4. The secant of theta is the hypotenuse over the adjacent, which is square root of 17 over 1. And last but not least, the cotangent of theta will be the adjacent over the opposite, which is 1/4. Now, the one thing we need to go back and look at is to actually look at the quadrant information here. Remember, our angle is in quadrant 2, which means some of these trig functions are negative. In quadrant 2, we know that the cosine is negative, the secant is negative, and the cotangent is negative. And so we will mark those three as being negative, and we'll leave sine and cosecant as positive. And this will give us our 5 remaining trig functions for this particular angle using a right triangle and the information about the quadrant to be able to determine which are positive and negative. Notice that we do get the same values as on the previous approach, which makes sense. So these two approaches are equivalent. You can use either of them whenever you encounter a problem like this. And it's sort of just a user's choice type of situation of which approach you prefer.